In this video, we're going to go over the basics of lag compensation before looking at an example in the next video. So remember, the big difference between our lag compensation and our PI compensator is that with our lag compensation, we're using passive elements. So again, we have this trade-off that this means it's going to be cheaper because we're just using resistors, capacitors, inductors as opposed to op-amps. However, the drawback of this is that we can't increase the system type, and therefore we cannot drive our steady state error to zero. So we have the same idea as our PI controller, except now we don't have that pole exactly at the origin. So same idea as our PI, but now pole is not at our origin. So if we look at that graphically in the S-plane, so we have our j omega and our sigma axes, our imaginary and real. So now we're going to have some PC, which is going to be here, and so we can call this negative PC, and we're going to have some associated zero as well, the same as we had with our PI controller, negative ZC. And so the reason I've written those as negative PC and negative ZC is that in a minute when we look at our block diagram, we can write those as positive values. So here we have a block diagram for what our lag compensator would look like. So of course we have our gain block K, we have our plant or process, which is represented by some zeros and poles, and then we have our compensator here. So again, notice that it's on the low power side of the system. And so because I had negative PC and negative ZC up there, I can write this as S plus ZC and S plus PC. So a couple things to note about this system is we can look at the plant and we can note that in this particular case, because we have an S to the 1 in the denominator, this would be for a type 1 system. So I've done that so we can talk about a specific error constant, but we could be more general and say that's S to the power of n as well. So we can make the same argument for, as we did with our PI controller, about our angle and magnitude of that compensator pole and zero. So same argument as with our PI case about angle contribution, angle and magnitude contributions. And remember, the thing we said was that the angle and magnitude from our zero is going to cancel out with the angle and magnitude from our pole. So we want these two to be canceling out. And so this is particularly, we're talking about for our compensator. So canceling out, but we said for that to be true, the pole and zero have to be close to one another. So in this case, we can say if ZC and PC are close to one another. And so if that's true, then we have relatively little change in our root locus, which means we're not changing the transient response significantly. So ultimately, this means we have minimal effect on our transient response. So minimal effect on our transient response, which is of course at the moment what we're trying to do. Again, we're going to come back later and see how we can adjust transient response and steady state error. But right now we're saying let's just focus on our steady state error and leave our transient response alone. Okay, so as I pointed out, again, this above diagram is a type 1 system. So let's go ahead and say that. So we have a type 1 system above. And because of that, we know our relevant static error constant is going to be KV. And so let's call our initial KV is KV naught. And so this is before adding the compensator. So let me actually move this down a little bit, or over here, and let's say this is before we add that lag compensator. And so what that means is we're just considering our gain and our plant. So we see we're going to have our KV naught. So remember, we had talked about previously, our KV is the limit as S goes to 0 of S times G of S, where our G of S is going to be this combination here. So we see the S is going to cancel out with this S in the denominator, and we're letting all of the other S's go to 0. So the result then is that our initial static error constant, KV naught, is going to be K times the product of the zeros, so Z1, Z2, up to however many zeros we have, divided by the product of the poles, so P1, P2, P3, so on and so forth for however many poles we have. Now, once we add the compensator in, so let's see, after adding our compensation, what we're going to have is some new static error constant, so let's call that KVN. Let me do capital N to be consistent with the notes. And so now we're considering all of this as our GEQ. So we're adding that compensator in. We're still using the same basic equation of limit as s goes to 0 of s times, let's just say GEQ to be general. And so again, the s is going to cancel out with this s here, and we're just going to have an extra ZC in the numerator and an extra PC in the denominator. So let's come down here and write that explicitly. So now we can say we have this initial part above, which was K times Z1 times Z2, so on and so forth. And now we've added this ZC term. And down here we have P1, P2, so on and so forth. And now we've added this PC term. And so what we can see is that this is equal to our initial static error constant, KV0, times this ratio of ZC over PC. And so, of course, as we saw from this initial diagram, our 0 is further to the left, which means that this value of ZC, positive ZC, is going to be greater than PC. So this ratio here is going to be a greater than 1, which means that this is going to be an increase in our static error constant value. So if we think back to our static, or not our static error, to our steady state error unit, we know that increasing KV is what we want to do. So increasing our static error constant is desirable because we recall that our steady state error, so steady state error for a type 1 system is equal to 1 over KV. So if we're increasing KV, that means that we're decreasing our steady state error. And of course that's a good thing. So we want to be decreasing steady state error. So again, increasing KV, decreasing ESS. So now we want to sort of focus on this here, and we see that our steady state, or sorry, our static error constant is being increased by this factor. So we have KV is increased by a factor of ZC divided by PC. So what we want is we want this factor to be large. So want this to be large. Okay, so at first glance, we say, let's make that really large so we reduce our steady state error. We can do that really easily just by making this ZC value really big compared to PC. However, we need to think back to our requirements in terms of our angle and magnitude contributions canceling out. We said that ZC and PC have to be close to one another. So keeping these two things in mind, we want to reduce the transient reduce the effect on the transient response by having that pole and 0 close to one another. At the same time though, we want our ZC to be much larger than PC to have this ratio be large and therefore have maximum reduction in our steady state error. So sort of the way that we can have both of those things, so our solution to that dilemma, is to put our ZC and PC near the origin. So put ZC and PC near the origin, which was kind of already where we would be going anyway, because to get this as close as possible to approximating a pure integration, we would want that pole near the origin. So for example, if we consider some numbers here, so let's say we put our pole at some point that's negative 0.001, and we had our 0, which is at some point negative 0.01. So now, of course, these are pretty close to each other, so they're almost essentially 0.01 apart. However, the ratio ZC over PC is equal to 10. So in that way, we can have a relatively large ratio while still ensuring that our ZC and PC are close together, ultimately indicating that we have a minimal effect on our transient response. And so in the next video, we're going to take a look at an example of designing a lag compensator to get a certain steady state error.